On this video, we're going to be finding the initial pH of each of these solutions. We're going to start with number one. Number one, remember, no matter what you have, you're always going to have either a strong acid or base, a weak acid or base, or a buffer. That's when you have a solution by itself. If you mix two things together and you ask yourself, is there a reaction? If the answer is yes, then you do stoich in moles. If the answer is no, then you go back to which of these do you have. So we'll start with number one. Number one, you simply have a container that has HCl and water. All right, so I'll try to draw a little picture here. In your cup when you did this lab, you had HCl, and then you added water. So you just have HCl and water, but remember the HCl concentration is going to be diluted because you took 5 of this and 5 of this. So the concentration of HCl is really going to be 0.05. You cut it in half. So you have a 0.05 molar HCl, which means you have a 0.05 molar H plus because it's a strong acid. And then all you have to do is take the negative log of that, 0.05, and you're going to get 1.30. So negative log of 0.050, that's going to be a pH equal to 1.30. This is your starting pH of this. Okay, the next one. You have just NaOH. NaOH is a strong base. So in your beaker, you just have some NaOH, and then you have water. So again, you diluted this, half and half, right? 5 of this and 5 of water. So then you cut it in half, the concentration. So that's going to be a 0.50 molar NaOH, which means you have a 0.050 molar hydroxide. And so when you take negative log of 0.050, you're going to get also 1.30, but remember that's the pOH equals 1.30. So 14 minus 1.30 is going to 12.70, and that's going to be the that's going to be the pH. So that's going to be the pH of the solution, which again makes sense because it's basic. So what we saw is that number one was a strong acid. Do that right here. And number two was a strong base. Now on number three, we're looking at HC2H3O2, which is a weak acid, and we're putting together diluting it with distilled water, so we know there's a weak acid. Again, if you have a strong or weak or a buffer, in this case we have a weak. How do you handle a weak? You do ice and Ka. So simply you could write HA goes to H plus and A minus. You're going to do ICE. Now be careful with your molarity. Remember, this is not going to be 0.1 anymore. It's going to be 0.05 because you diluted it with water. 0, 0 minus x plus x plus x. So here you have this 0.5 minus x. And now you're going to set that equal to Ka. So Ka equals x squared over, I wrote that wrong, sorry, 0.05 over there. 0.05 minus x. We're going to ignore this because it's a very small k, so we don't need to worry about the minus x for that. And of course, we remember that the Ka is 1.810 to the minus fifth. So when you take 1.8 times 10 to the minus fifth times 0.5 and square root that, you're going to oh dear, I did it wrong again. 1.8 10 to the minus fifth times 0.05, and then we're going to square root that. You're going to get 9.5 10 to the minus fourth. That's going to be the H plus concentration. So then you're going to take negative log of 9.5 times 10 to the minus 4th, and you're going to find that to be 3.02 as your first pH in this solution. So don't forget, if you were going to draw a picture, you have here your acetic acid, and then you just added some water to it. So now you know that you diluted it, and that's why the concentration went to 0.05. Now we're going to take a look at number 4. We have a little cup, and then here what you did is you took NH3 and put it in here, and then you added water. So you diluted that. So what do we have? We have a weak base. NH3 is a weak base. So how do we handle that? Ice and Kb. So we do NH3 plus HOH yields NH4 plus and hydroxide. We're going to do an ICE calculation. This is now again going to be 0.05 because you cut it in half. We don't care about the water. 0, 0, minus x plus x plus x. So 0.05 minus x, x, x. And we're going to set that equal to Kb of ammonia, which happens to be 1.8 10 to the minus 5th equals x squared over 0.05 minus x. Again, ignore the x. So we are going to get the same x as we got before, but remember, this is the concentration of the hydroxide. So when you take the negative log, I'll just write OH minus, that equals 3.02, but that's the POH, so we do 14 minus 3.02, and we're going to get 10.98 as our pH, which is basic, which makes sense. Now on number 5, we have a strong acid, HCl, and we have a strong base, NaOH. So anytime you add two substances together, you have to ask yourself, is there a reaction? If it's ever an acid and a base that are not conjugates, the answer is yes, and when the answer is yes, you do stoic in moles. So I'm going to write that down, reaction, yes, so we do stoic in moles. So we have our H plus, that's all that matters from the HCl. We have our Cl minus, that's our OH minus, that's all that matters from the the NaOH, and then you're going to make water. And because this is going to be limiting reagent and moles, one of them is going to run out. In this case, they both run out. If you want to get the moles of this, remember how you do that? So let me backtrack here real quick, do the picture so we see that. Here's the picture. So you have HCl right here, and you have NaOH right here. So we added NaOH into HCl. We actually added the exact amount for both. So when we're all done, what our beaker is going to look like is just water. And here's how it's going to work. We're going to do molarity equals moles over liters. So let's do that over here. Molarity equals moles over liters. The concentration of the HCl was 0.1. The amount was 0.005. So when you do the math for this comes out to be 0.0005 moles. And that's going to actually be the same for the NaOH as well, because it's the same calculation, same numbers. So I'm going to write that, 0.0005 moles. And the NaOH is also going to be 0.0005 moles. And then we're not really going to care about the water. So they're both going to run out at the same time. So now you're just left with water. And as you know, water is neutral. So you're just going to do negative log of 10 to the minus 7th for the H plus. Okay, so we'll do that. This is going to be negative log of 1.0 10 to the minus 7th. 7.00 is the pH, and this is actually going to be a neutral solution once we're all done, because the H and the OH both ran out. Okay, number 6, we're going to look at that, and we're going to see that this is a weak acid and its conjugate base. So the question is there a reaction? The answer is no. So then what do we have? We have a buffer. So when we have a buffer, we use the buffer shortcut. So H plus equals Ka times A over B. You're allowed to use molarity or moles for this. So if you know that the Ka is 1.8 for acetic acid, 10 to the minus fifth. Now the acid is not going to be 0.1 anymore. Remember, it's diluted because you mixed it with the other solution. So this is really going to be 0.05 molar. Interestingly, if you forgot that, you would actually still get the right answer, but you could bet that questions will be designed so you can't do that. So this is the molarity of the C2H3O2 minus. This is the molarity of the HC2H3O2. You'll notice that that's going to divide out. So the H plus is going to be that when these divide out. So you're going to take the negative log of H plus, and that should be 4.74 as your pH of the buffer. On number 7, we have a weak base and its conjugate acid because ammonium chloride will dissociate. Therefore, we have a buffer, and when you have a buffer, we use the buffer shortcut. Remember that this is not going to react when they are conjugates of one another. So the buffer shortcut, I'm going to use the OH shortcut simply because we know the Kb. So that's going to be B over A. The Kb of ammonia is 1.8 10 to the minus fifth. We know that the base molarity is 0.1, but we diluted it to half of that concentration with the molarity, with the NH4 plus. So therefore, we're going to cut both of those in half. You're going to notice that the OH is going to be the same as the Kb because those are going to divide out. And then you're going to take the negative log of OH minus, which is going to be 4.74. But that's the POH. So you have to take 14 minus 4.74 to get 9.26 as your pH. So if you want to draw a quick picture of this, you're going to see that the little cup is going to have your buffer in it, and when you put this together, it's just going to be a buffer, NH3 in the bottom, and NH4 plus as well. There's no reaction because they're conjugates. Now we're going to move on to the next one, which is acetic acid and NaOH. So what we notice is that we have a weak acid and we have a strong base. And make sure this is printed on your paper because it didn't print out originally with mine. So now we're going to look at this and say, is there a reaction? Okay, got ahead of myself here. So is there a reaction between a weak acid and a strong base? The answer is yes. Stoichiometric moles. So let's write the reaction. I'm just going to abbreviate HA for my weak acid. That's going to react with the hydroxide to make water. And you have the conjugate base of your acid, which is A minus. This is going to be a limiting reagent, ICF. You have to work in moles. So to get moles, remember you're going to do molarity equals moles over liters. Let me just do this in red so we see what we're doing here. I'll set it up for you. Molarity equals moles over liters. So if we take a look at the acetic acid, it was 0.1 molar. We had 5 milliliters, so that's 0.0005. And then, I'm sorry, 0.005. Got ahead of myself again. Just 2 zeros. 0.005. And then when you do the math for this, for the top, you're going to get 0.0005 moles. So that goes over here. And then you're going to do the same thing for the OH. But be careful, because the OH was 0.1 molar. However, you only used 2.5 milliliters, so 0.0025 liters. So that's going to be 0.00025 moles. So that goes over here. And then we don't care about the water. This was a 0. So the running out is the OH, the limiting reagent. 3 zeros there. Minus 0.00025 and plus 0.00025. So when all is done reacting, you have A minus, you have HA. And you ask yourself, what do I have? A strong, a weak, or a buffer? I have a buffer. So now I use the buffer shortcut. So the buffer shortcut I'm going to use is going to be the H plus, since I know the Ka of acetic acid. It's going to be 1.8 10 to the minus fifth. We're going to copy down the acid, which is the 0.0025. 0.00025. And then the base also 0.00025. And they're going to divide out, and you're going to take the negative log, and you're going to find negative log of H plus equals 4.74, and that is the pH of this buffer. I just want to mention something about millimoles. Some people might like millimoles better because there's a lot less zeros involved. So if you were going to do this calculation for the NaOH, you could have done 0.1 molar equals 2.5 milliliters, and then you solve for millimoles on top, and you would have gotten 0.25. Okay, so millimoles over milliliters is also molarity, if that's helpful to you. Here's a quick picture to show you what we're doing here. So you originally had HA in here, then you added OH minus into it, it reacted, so you did stoichiometric moles, and when you were all done, you were left with HA and A minus, which is a buffer. So this is a buffer, and we also understood that number 7 was also a buffer. It was not neutral, it was just a buffer. Now we're on page 6. We see that we have a weak base and we have a strong acid. The first question we ask, are these going to react? The answer is yes. So we do stoic in moles. Quick picture. You have your little cup. Inside your cup you have NH3. To your cup you're going to add H plus. They're going to react. So we'll do our stoic in moles. H plus is going to react with the NH3 to make NH4 plus, which is the conjugate acid of NH3. So we're going to do our ICF chart. We need to know the moles. So again, we're going to use molarity equals moles over liters. For the base, the NH3, we have 0.1 molar. All right, I'm going to just do millimoles just for fun. Okay, if you don't like it, you could use liters. But here are the milliliters, and the ammonia was 5.0. So then we solve, we get 0.50 millimoles. So I'm going to write that here, 0.50 millimoles. Let's do the H plus. That was a 0.1 molar, but I only used 2.5 milliliters of that, so 2.5 milliliters. That's going to be 0.25 millimoles. and we don't have any of this ammonium to start. We're going to run out of the H plus, so minus 0.25 minus 0.25 plus 0.25, so that's going to be a plus 0.25, that's going to be a 0.25, and that's going to be a 0.25. No, sorry, this one runs out, the H plus runs out, so that's going to be a 0. So now we look at what we have left. We have a weak acid and a weak base conjugate, so it's going to be a buffer. So now I look at this and I say I have a buffer shortcut. I'm going to go ahead and use the OH minus concentration shortcut. So KB in times B over A. KB is 1.8 10 to minus fifth. The base is this 0.25. That's in millimoles. You're allowed to use moles, millimoles, or molarity for the shortcut. So this is also 0.25 millimoles. So you see millimoles kind of make it less dramatic with the zeros. Okay, so you're going to take the negative log of OH minus, which is going to be, of course, 4.74. But then you take 14 minus that, because that was the POH, and you're going to get 9.26 as your pH. So you turn this into a buffer. So now the little cup looks like this. We have NH3 in it, and we have NH4 plus. So we have created a buffer.